The minimum acceptable resistance to earth for a surface ground is 25 ohms. This requirement is crucial for ensuring electrical safety and providing a low impedance path for fault current to return to the source. This low impedance path facilitates the operation of overcurrent protection devices such as circuit breakers and fuses. When a ground fault occurs, a large current will flow through the grounding system, tripping the breaker or blowing the fuse, thereby disconnecting the faulty circuit and preventing electrical shock hazards. Grounding is a critical aspect of electrical system design and installation, serving several important functions. Firstly, it provides a low impedance path for fault currents. Secondly, it helps to stabilize voltage to ground during normal operation. Thirdly, it minimizes the risk of electrical shock. The grounding system typically consists of a grounding electrode, which is a conductive rod, plate, or other device buried in the earth, and a grounding conductor, which connects the grounding electrode to the electrical system. The grounding electrode provides a direct connection to the earth, allowing fault currents to flow back to the source. Several types of grounding electrodes are commonly used, including ground rods, ground plates, and concrete-encased electrodes, often referred to as U for grounds. Ground rods are typically copper or copper-clad steel rods that are driven into the earth. Ground plates are copper or other conductive metal plates that are buried in the earth. Concrete-encased electrodes are bare copper conductors that are encased in concrete foundations or footings. The choice of grounding electrode depends on site conditions, soil resistivity, and local codes and regulations. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity is desirable for effective grounding because it allows fault currents to flow more easily through the earth. Soil resistivity varies depending on factors such as moisture content, temperature, and the presence of minerals and salts. In areas with high soil resistivity, it may be necessary to install multiple grounding electrodes or to use soil treatment methods to reduce the resistance to earth. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding electrical systems. Article 250 of the NEC covers grounding and bonding requirements. The NEC specifies the types of grounding electrodes that are permitted, the minimum size of grounding conductors, and the methods for installing grounding electrodes. The NEC also requires that the resistance to earth of a single grounding electrode not exceed 25 ohms. If the resistance exceeds 25 ohms, a supplemental grounding electrode must be installed and bonded to the original electrode. The supplemental electrode must be located at least 6 feet away from the original electrode. Measuring grounding resistance is an important part of maintaining a safe and effective grounding system. Ground resistance testers, also known as earth ground testers, are used to measure the resistance to earth of grounding electrodes. These testers typically use a 3-point or 4-point test method to measure the resistance. The 3-point method involves driving 2 auxiliary ground rods into the earth and measuring the resistance between the grounding electrode and each auxiliary ground rod. The 4-point method is similar to the 3-point method, but it uses 2 current electrodes and 2 potential electrodes to measure the resistance more accurately. Proper grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault currents, which helps to trip over current protection devices and prevent electrical shock hazards. Bonding is the process of connecting all metal parts of an electrical system together to create a common ground potential. Bonding helps to minimize voltage differences between metal parts, which can reduce the risk of electrical shock. In addition to grounding electrodes and grounding conductors, bonding conductors are also used to connect metal enclosures, equipment frames, and other metal parts of an electrical system. Bonding conductors must be sized according to the requirements of the NEC. The NEC specifies the minimum size of bonding conductors based on the size of the circuit conductors. Grounding and bonding are often used together to create a comprehensive grounding system. A properly designed and installed grounding system will provide a safe and reliable electrical system. Several factors can affect grounding resistance, including soil moisture, temperature, and the presence of corrosion. Soil moisture is a critical factor because water is a good conductor of electricity. Dry soil has a much higher resistance than wet soil. Therefore, grounding resistance can vary depending on the weather and seasonal conditions. Temperature can also affect grounding resistance. As the temperature decreases, the resistance of the soil increases. Corrosion can also increase grounding resistance. Corrosion can occur when metal parts of the grounding system are exposed to moisture and chemicals in the soil. To minimize the effects of corrosion, it is important to use corrosion-resistant materials for grounding electrodes and grounding conductors. Regular inspection and testing of the grounding system can help to identify and correct problems before they become serious. Grounding resistance should be measured periodically to ensure that it is within acceptable limits. Visual inspections should also be performed to check for signs of corrosion or damage to the grounding system. If any problems are found, they should be corrected immediately. Grounding and bonding are complex topics that are covered in detail in the NEC. Electricians and other electrical professionals should be familiar with the requirements of the NEC in order to design and install safe and effective grounding systems. Article 250 of the NEC provides detailed information on grounding and bonding requirements. The NEC is updated every 3 years, so it is important to stay current with the latest edition. In addition to the NEC, other standards and regulations may also apply to grounding and bonding. For example, the Institute of Electrical and Electronics Engineers, or IEE, publishes standards for grounding and bonding of electrical equipment. Local codes and regulations may also have specific requirements for grounding and bonding. It is important to comply with all applicable standards and regulations to ensure a safe and reliable electrical system. Grounding is not only important for safety, but it is also important for the proper operation of electrical equipment. Improper grounding can cause equipment malfunctions such as erratic operation, data errors, and premature failure. In some cases, improper grounding can even damage equipment. Therefore, it is important to ensure that all electrical equipment is properly grounded. Grounding is a critical aspect of electrical system design and installation. A properly designed and installed grounding system will provide a safe and reliable electrical system. Regular inspection and testing of the grounding system can help to identify and correct problems before they become serious. The 25 ohms requirement for grounding resistance is a critical safety standard. Ensuring compliance with this standard is essential for protecting people and property from electrical hazards. Grounding systems are not static. They can change over time due to environmental factors, corrosion, and other issues. Therefore, regular testing is crucial. A ground resistance tester is the tool used to measure the resistance to earth. These devices use various methods, such as the 3-point fall of potential method, to accurately determine the grounding resistance. When measuring grounding resistance, it is important to follow the manufacturer's instructions carefully. The placement of the test probes is critical for obtaining accurate readings. Also, it is important to ensure that the grounding system is isolated from other electrical systems during the test. Common grounding mistakes include using undersized grounding conductors, failing to properly bond metal parts, and neglecting to install supplemental grounding electrodes in areas with high soil resistivity. These mistakes can compromise the effectiveness of the grounding system and increase the risk of electrical shock. Correcting these mistakes is essential for ensuring electrical safety. The grounding system works in conjunction with overcurrent protection devices, such as circuit breakers and fuses, to protect against electrical faults. When a ground fault occurs, the grounding system provides a low impedance path for the fault current to return to the source. This high current causes the circuit breaker to trip or the fuse to blow, disconnecting the faulty circuit and preventing electrical shock. Without a properly grounded system, the fault current may not be high enough to trap the overcurrent protection device, resulting in a dangerous situation. Grounding requirements can vary depending on the type of electrical system and the application. For example, grounding requirements for industrial facilities may be different from those for residential buildings. It is important to consult the NEC and other applicable standards to determine the specific grounding requirements for each application. The principles of grounding remain the same, regardless of the application. Grounding is an essential safety measure that should never be overlooked. Understanding the importance of grounding and following proper grounding practices can help to prevent electrical accidents and save lives. The minimum grounding resistance of 25 ohms is a key factor in ensuring electrical safety. By maintaining a low resistance to earth, the grounding system can effectively protect against electrical shock and equipment damage. The NEC provides detailed guidelines for achieving this grounding resistance and ensuring a safe electrical system. Regularly testing and maintaining the grounding system is essential for long-term safety and reliability.